Okay. Thanks very much, everyone, for coming on such short notice. It's kind of an impromptu talk. It's going to be a bare bones talk. It's going to be very simple. We'll just show you a few slides, hopefully about 40 minutes. The first half will be mine. The second half will be Eric's. And then we'll show you a movie. It's a pretty cool movie at the end of the lecture. And then we'll open the floor for discussions, questions. Please don't ask questions which are too difficult. Okay. So what is shown on the screen is one of the LIGO sites in the state of Washington, in the desert. As you see, there is a station, central station, and there are two arms. Each arm is 4 kilometers long, or if you're an American, it's 2.5 miles long, each of the arms. And I'll talk about a little bit about what's inside the station, what's inside the arms later on. But first, I want to talk about the reason why we built such a machine. And this story has begun 100 years ago, a little bit more than 100 years ago, with Albert Einstein publishing his theory of general relativity in 1915. There were other things going on in Europe in 1915, but Einstein was very much focused on trying to understand the nature of space and time. And he comes up with what at the time was a very radical idea, saying that space and time form a single space-time, and moreover, this space-time is not flat. It is curved, and it is curved under the influence of matter. And all of Einstein's theory is contained in this simple-looking equation, but the left-hand side of this equation represents geometry of space-time, the curved geometry, and the right-hand side represents the influence of matter. And Einstein says that the geometry and matter are intimately related. There is a very deep connection between them. And in particular, the matter tells space-time how to curve, as is shown on this cartoon where the Earth is creating deformation of space-time continuum around itself. And space-time, in turn, tells matter how to move. So these two have very deep relationship between each other. Now, for the rest of my talk, I will have no matter. I will only talk about essentially an empty space-time. But this space-time will do crazy things. So if you have space-time by itself, it can also move. In particular, you can have ripples in space-time, and you can have punctures. Ripples in space-time are called gravitational waves, and punctures are black holes. So let me give you, if you take anything away from this part of the lecture, it's this simple truth which follows from Einstein's theory, that space-time can move and stretch and squeeze, and it can have propagating ripples and permanent punctures. The punctures are truly permanent. You can't heal them. And these punctures are black holes. So it took a while to understand through the work of many very intelligent people, it took a while to understand that black holes are actually very simple objects. In fact, in some sense, they're the simplest objects in the universe. Black holes, all of the black holes which exist in the universe, and I have a drawing of a black hole, are described by just two numbers. The first number is its mass, how much the black hole weighs, and the second number is its spin, how quickly it's rotating. And I've drawn like a little map of a black hole here. So there are several regions around the spinning black hole. The region in yellow is a so-called ergosphere. An ergosphere is the region where a black hole applies itself to the outside world. It can do work. It can launch powerful jets that we see coming from centers of galaxies or from microquasars in our galaxy. If you lower a load in the holes into this ergosphere, these holes will be forced to rotate with the black hole no matter how hard you pull on it. And that's how black hole does work on the outside world. Then on the inside of the ergosphere is a horizon, and inside the horizon there is no return. You are completely causally disconnected from the outside world. So this is the very simple structure of a rotating black hole, which by now is exceedingly well understood by theoretical physicists and mathematicians. Let me just show you a drawing, a cartoon drawn by Thrane of what black holes look like. So this is the representation of the curvature of the equatorial plane drawn through a black hole. And you see that there is a circumference like so, but the diameter, the radial direction, is much longer than what you would have guessed just by going around this black hole. And there is a horizon, which is a surface of no return. And you can see this cartoon, this gentleman who is just outside the horizon can still send signals to the outside world. But this gentleman who is inside the horizon is no longer unable to communicate to the outside world. And let me just show you also the cartoon, a sketch of a rotating black hole. It's basically the same structure. You have a horizon, except for the ergosphere is represented by this region of space drag. And one of the features, one of the crazy features of black hole spacetimes is that the radial direction, what we think normally as radius, turns into time direction. So the radial coordinate becomes time-like, and the time inevitably pushes you towards the singularity. So anybody who falls inside the horizon is going to be dragged towards the singularity and face its ultimate fate. Nothing can survive the singularity because the tidal stresses are infinite. Yes, please?
How far away is the closest black hole?
That's a very good question. I think the truthful answer is that we don't know. We only know about the black holes which are active in X-rays. But we are pretty sure about the closest supermassive black hole, which is the Sagittarius A-star black hole, the center of our galaxy. And this is about 25,000 light years away. Any other questions at this point?
You mentioned the drag effect. Is it, will that slowly slow the rotation of the black hole itself, like the drag that wave motion on the surface of the Earth with the moon, that slows, there's energy lost there. What about with the rotation of the black hole, will that eventually slow?
That's a great question. If a black hole does work on the outside world, the only way it can do work is by expanding its rotational energy. And in fact, it slows it down. Okay, but you have to gear it, right? You have to put it in gear, which is typically done by magnetic fields in nature. All right, so let me also show you, so these are kind of cartoons of deformed space-time, but these are scientific cartoons. Let me show you an artistic cartoon, which I think is kind of cool. This is an artist's impression of what really strongly deformed space-time would look like. And you can see many interesting things here, but in particular you can see pictures of rotating black holes. You also have wormholes which connect different locations in this kind of space-time sheets. And you have propagating ripples, which are presumably gravitational waves. Now, back to science. As I explained to you, the simplest object in the universe is a black hole. And you can ask a question, what is the simplest dynamical process that you can have in the universe? And the answer is obvious. It is the merger of two black holes. It is how two black holes interact with each other. Let me show you an illustration of a numerical simulation done by some clever people with big computers. And what you see on this picture is two black holes orbiting each other. You see deformed equatorial sheets which go through both black holes. And at the bottom, you see the gravitational waveform which comes away. You see those ripples which are propagating away. These ripples are gravitational waves. These are perturbations in the curvature of space-time itself. No matter here, just empty space-time behaving in crazy way. You see that the horizons of these black holes are about to touch. and they're about to merge into a single one. So this is just frozen for your benefit so that you see how it happens. The gravitational waveform goes through its maximum, and after the single black hole forms, it rings down. It shakes out any kind of perturbations, and the gravitational wave becomes flat. And this is the characteristic gravitational wave signal that LIGO is looking for from mergers of two black holes. And you will see later on, Eric Thrane will show you how beautifully the LIGO measurement is in agreement with this gravitational wave which is coming from this pair of black holes. Now, a little bit about gravitational waves. So I showed you some crazily deformed spacetimes, but of course by the time gravitational waves propagate to us, they're actually very weak. So this is what gravitational waves would do to matter here, to the outside world. And I show here a ring of particles, and I show how gravitational wave would deform this ring of particles. Basically, it takes a circular ring and deforms it back and forth into elliptical shapes. This is hugely exaggerated, but this is just an illustration of what the gravitational wave would do. And these two different rings correspond to two different polarizations. You might remember from your high school physics courses that electromagnetic waves have two polarizations. The same is true for gravitational waves. They come in two different polarizations. Now, if you ask a question, how big this perturbation is, it's tiny. It's really, truly spectacularly tiny. And somehow Eric has erased this very important expression for h. But I'll tell you what it is.
If you click twice, it will appear. One more.
OK, I'll tell you what it is. It is very small. It's very easy to compute. And if my laser pointer, it's good that I don't actually work as an experimentalist on LIGO. So this h is basically the black hole size divided by the huge distance to the merger of the black hole. This is how you estimate this deformation. This is a relative deformation. And it comes to about 10 to the minus 22. This is an incredibly small number. And just to understand how small it is, let's multiply this number to get the typical displacement of the LIGO arm. I told you the LIGO arm is a few kilometers, 4 kilometers. If you multiply by a few kilometers by 10 to the minus 22, you get something of the order of 10 to the minus 18 meters. This is a very small number. Let me tell you just how small. The size of an hydrogen atom is about 10 to the minus 10 meters. So this is a picture of, conceptual, minimalist picture of a hydrogen atom. At the center of a hydrogen atom, you have a proton. The proton itself is very small. It has a size of 1 Fermi, or about 10 to the minus 15 meters. The displacement of the LIGO mirror that we have to measure is 10 to the minus 18 meters. Are there any people here who are younger than 15 years old? Can you please lift your hands? Now, can any of you young people work out what fraction of a proton radius, what fraction of 10 to the minus 15 meters is the displacement of the LIGO mirror? What is the fraction? What is the ratio of this number divided by this number? Yes? 1,000. Very good. That's incredible. We have to measure the displacements which are 1,000th of the size of the proton. That's what we have to do to measure gravitational waves. Does it sound to you incredibly difficult? I hope it sounds to you incredibly difficult because it is difficult, and that's why we have to build these amazing machines. So this is a picture of the second site in LIGO, which is 4 kilometers long, and now it's not in the desert in Washington, the state of Washington, but it's in a swamp in Louisiana, the state of Louisiana in the United States. And let me just tell you a little bit more about what LIGO is. Now, LIGO is a project, an expensive project, which has demanded not just expense in money, which is considerable from National Science Foundation, but also expense in intelligence and expense in commitment and many other types of expenses. But what it is inside, so this is how it works. Remember, there is this gravitational wave which displaces displaces these masses. And inside this interferometer, you have two arms. Each of these arms has mirrors, and the mirrors are penduli, which are suspended like this. I call them freely falling because we want to approximate as closely as possible with this penduli, the freely falling masses, as is shown in this ring. Now, when gravitational wave comes, it changes the length of these arms in the opposite direction. You see, when this arm becomes longer, then the perpendicular arm becomes shorter, and then the other way around. So this oscillating ring is displaying this. So now, when the laser light, which is shown here, returns, the laser light is injected by this laser. There is a beam splitter, and half of it goes into one arm, gets captured, circulates for a while. The other half goes into the other arm, gets captured, and circulates for a while. About 100 bounces in each arms. Then the light leaks out. When it leaks out, these two light beams talk to each other, and each of them shares an impression of what happened inside each of these arms. And if they experience different lengths, they start disagreeing with each other, and some of it leaks out into this detector. Okay, it's the result of this disagreement. So when these two light beams are fighting due to the presence of gravitational wave, then this detector detects this difference. Now, this is a very ingenious scheme, which is called the interferometric measurements. Now, this is just conceptual. Let me show you the type of things that LIGO people have to deal with, which is this is kind of the most technical slide that I'll have, but just for engineers and people with technical backgrounds. This is a compendium of sources of noise that we have to deal with in LIGO. So on the x-axis, you have frequency, right? This is the frequency that of gravitational waves that you're trying to measure. And you can see 10 hertz, 100 hertz, 1,000 hertz. It's all kind of audio band, luckily for us, because Eric will sing gravitational waves for you later on. And on the y-axis, you have the amount of noise, which is represented by some quantity. Don't worry about this, but see how many noise sources. Each of this curve represents a noise source that we have to battle with in order to understand and bring this detector under control. And it takes generations of scientists to battle this noise, to understand it, and actually control it. And now I'm going to after describing this and describing to you, roughly speaking, the experiment, I'm going to hand you over to Eric for the most exciting part of the talk, which is recent discovery. Yuri.
So thank you to Yuri for setting the stage, telling us about gravity, about black holes, about gravitational waves. For the remainder of the talk, I'm going to put you through the experience of discovering gravitational waves as you would have experienced it, I hope, as a member of the LIGO Science Collaboration. So we have about 1,000+ members in LIGO. This room, if we add us to the LSC, won't increase our numbers that much. So you're all LIGO members now for the next 15 minutes. And we'll begin the discovery in the control room. This is the photo of the control room of the LIGO Observatory in Livingston. And if you remember this building from Yuri's shot of these arms. This is at the vertex of one of these arms with the two big 4-kilometer-long tunnels. If you go inside here, it's actually quite a big building. There are screens and operators who are students who sit at these computers. They monitor the detectors. And it's a great place to visit if you're ever in the States and have the opportunity to go there. It's a little bit like Homer Simpson's nuclear plant desk. There are screens and buttons all around you. It's impossible to know what any of them mean. But I want to talk about two screens in particular on this photo, and that is these ones. If you can kind of make out, this is showing you how the detector is performing. They're just general figures of merit, saying how good is the detector operating right now as you sit in the room. And I'm now going to pull for you we're going to look at the screenshots that you would have seen if you had been in the LIGO control room the night that we detected gravitational waves. So there are quite a few plots here. We'll start on the right-hand side. It's a little bit difficult to read all the axes off on this plot, but basically this axis is telling you what time of day it is in hours. So it's just the time. And this axis is telling you how far away can you see a typical gravitational wave signal. In this case, the source of gravitational waves that we're wondering about are two neutron stars colliding together. And at this moment, we could see them 230 million light years away. So this is very good. This is, the detector was operating. We hadn't officially begun taking our official first science run data yet, but we were commissioning it. We were preparing to take our data, and it was clearly going to be a good detector. But you can see it periodically turns red here on the bottom. During these times, the detector has dropped out or lost lock. The laser beams in each arm are no longer talking to each other. They've disagreed too much in Yuri's language, and we've completely lost the ability to measure gravitational waves. But it's coming on and off. It's kind of like a finicky old television or something. Here then, this is the top one is for the LIGO Hanford Observatory. The bottom one is for the LIGO Livingston Observatory. And this black arrow indicates when something very special happened. At this moment that this arrow indicates, a gravitational wave from two black holes smashing into each other passed through the detectors and left its imprint on our data. And so we'll look at that in a moment. On the left-hand side of this slide, you can see the strain noise curves that these two detectors were measuring at about the time that this event took place. And Yuri showed us a slide a moment ago showing that we needed to get down to strains of 10 to the minus 21 or thereabouts. And at this particular moment, we had excellent strain sensitivity. But you'll notice that we got a little bit lucky. The Livingston detector had only been on for about an hour when the event happened, and then we lost lock a few hours after it. So if nature had been cruel and given us a gravitational wave signal here or here, we would have only seen it in one detector, and we might not have been able to know that we had actually seen it. So here now, remember, we're LSC members. We're going to watch these events unfold live. This is a minute-by-minute play-by-play of the event. So we're in Australia. We're going to watch this from Australia. And at 7:50 in the evening on September 14th of last year, gravitational waves swept through the detector. Within 3 minutes, a computer program that was analyzing the data noticed this and sent out emails to people. And people's pagers or cell phones went off. They received automated email. So a computer knew about this within 3 minutes. And immediately, people began looking at the data. One of these people, about an hour after he had gotten his text alert, knew something serious had happened. We hadn't officially started taking our real data yet, but it looked very compelling. So he sent a carefully crafted email to 1,100 people. And you want to make sure you get those emails right. And he entitled, the subject of this email was "Very Interesting Event." Immediately, all over the world, and we're going to live this in real time now, people are in different time zones. Some of them are waking up. Some of them are getting ready to go to sleep. They have their email in front of them, and they see this email, "Very Interesting Event." We're clicking on it all over the world, seeing this, looking at the data that I'm about to show you on the next slides, seeing for the first time together, as this international collaboration, this massive discovery. My own little role in this, at 9:17, one of my jobs was to insert fake signals into LIGO in order to test that we could detect them. And at 9:17, I said, "This isn't a test. I didn't do this. So continue to take it seriously." By, let's see, what's the timestamp here? 11 at night, Paul Lasky, who you'll be hearing from during the panel session, and I were gossiping. "How excited should I be?" Paul asked. And I wasn't yet, I was conservative, pretty excited. But 2 hours later, we were pretty thrilled. It was beginning to sink in. So why were we so excited? Why were people all over the world not going to sleep this night? What were we looking at? Well, let's look at some plots. So this is going to be the top row we'll start with. This is strain data. So this is what the detector measures. It's essentially just measuring how much the space-time is deformed from this gravitational wave, how much longer is one arm than the other as a function of time. So it's a little bit like an audio recording. It's just some signal as a function of time. And you see it starts off kind of just like random, and then it develops these wiggles. And this should look similar if you remember the video that Yuri played showing the gravitational wave signal from a binary black hole merger. This is it, but real. This shows the Hanford detector in Washington, and this shows the Livingston detector in Louisiana. And on the right-hand side, you can see the blue and the red signal on top of each other. This shows that these two detectors on opposite ends of the United States saw the same signal. Space was squeezed the same way at roughly the same time. And this can only happen if a gravitational wave passes through them. Moreover, the shape is exactly what we would have expected from general relativity. So what does these wiggles mean? What's happening as these wiggles, how can we interpret them physically? So here we'll now take this is the reconstructed waveform that we believe was in our data, so all the noise has been taken out of it. And we can look at this waveform that we detected with LIGO and say what's taking place at each stage. We can relate what we actually see in the data with what we saw in Yuri's movie earlier. So there are 3 stages of any binary coalescence, is our fancy term, when 2 black holes smash together. First, they undergo a phase of in-spiral where they slowly get closer and closer together. Then they merge and they form a single black hole. And finally, they ring down. Now, Yuri told us that he had a slide up that said no hair theorem. And the no hair theorem says black holes have no hair. They only can have 2 numbers that describe them. So if they have anything sticking out, any funny hairs sticking out, those hairs have to get shed. The hairs have to be radiated away in gravitational waves. So here is the hair loss period. And this is where that hair is shaken off. Now, it's hard to imagine how dramatic this would have looked up close if you'd been right on top of these black holes. But in order to get some sense of what this was like, we'll look at this bottom plot. This is plotting 2 things at once as a function of time. So here is time passing, and it's only about a half a second. All this is going to take place in less than a second, okay? And the green curve is on the left-hand side here. That's showing the velocity of these 2 black holes as a fraction of the speed of light. And you see that when they enter the LIGO band, they're already moving about 30% the speed of light. So these black holes are going fast. And when they finally coalesce, smash into each other, and form a single object, they're moving at almost 60% the speed of light. We also see them getting closer together. That's this black curve. And it's measuring how distant they are in something called Schwarzschild radii, which is the sort of the characteristic width of the black hole. And you can finally see they get so close that it doesn't make sense to talk about them as separate objects anymore. So here now, as a preface to the singing that will certainly take place during question and answers period, we'll hear some audio and video of what this signal looks like. So I'm going to play a little, very short movie, and you'll see the waveform, you'll see the data, and you'll also hear a sound. And this is quite remarkable. If you imagine you're sitting in the control room that we looked at earlier, when this happened, the control room actually has speakers in it. And you can put these speakers on and actually listen to the hum of the gravitational wave detector. You're listening to the deformation of space-time. And that's because the signals that we're looking for have frequencies which are similar to the frequencies you can hear with your human ear. So you're actually going to hear the gravitational wave signal. You'll hear it in 2 sets of 2. So the first 2, it's going to repeat. First, you're going to hear the actual sound of this gravitational wave chirp, it's called. And then it will be sped up. The first one's kind of low frequency, and we don't have great speakers in here, so it's just going to sound like a whump. But the second time, you'll hear it chirp. It'll go from a low sound to a high sound. So we'll listen to it now. Are you ready? Could you hear it a little bit? We'll have a demonstration, a verbal demonstration later. So that was what everyone was so excited about. And this happened back in September. We didn't announce the results until much later, and one of the things we had to do was be absolutely certain that this was real, but we also wanted to work out all the astrophysical implications. What is this event telling us about the universe? So I'll give you a few highlights now to sort of put this in perspective. So first of all, how far away was this merger? It turns out it's 1.3 billion light years away. So when these two black holes merged, there was unicellular life on Earth, and multicellular life would not evolve for another 600 million years, roughly. This is a long time ago. And it consisted of two black holes that each weighed about 35 times more than our own sun. And they created a remnant of about 60 times the mass of our sun, the black hole that they formed. Where on the sky did it happen? It was in the southern hemisphere, so it came from down under, we can say. We know that the black hole, so just imagine you have these things spinning. It could be oriented to you like this, which is edge on, or it could be face on. We know it was face on from the signal it gave us. And if we look at where it is in the sky, we can say that it was somewhere in this banana shape. This is very, compared to regular astronomy, this is a very poor idea of where it is in the sky. So the size of this is much bigger than the size of the moon. So we don't have a good sense of where this came from, but just this rough idea. At its peak, the merger produced a gravitational wave strain of 10 to the minus 21, which displaced the mirrors of the interferometer by 2,000ths of a Fermi, of a femtometer. I mentioned the peak speed of the black holes was about 60% the speed of light. How much energy was radiated in gravitational waves? So recall, the gravitational wave signal lasted significantly less than a second. It was in our detector's band for about 0.2 of a second. During this time, there was the equivalent of 3 solar masses of energy radiated. So what does this mean? This means that if you took our sun and then took another sun made entirely out of antimatter and collided them together, so they immediately just turned to pure energy and radiated away. So right now our sun's burning very, very slowly, but this is an instantaneous almost release of energy. That would still have less energy in that blast than was produced in gravitational waves in the final 0.2 seconds of this merger. So this is a tremendously energetic event. The black hole that was left over was about 180 kilometers in diameter, which could easily fit it in Victoria. It's about a little bit further than the distance to Bendigo from Melbourne. We'll get to hear in a moment from a panel of our members of LIGO who work here at Monash University. And well, I guess we'll introduce them when they come up. But this is our LIGO team smugly posing for a photo when we knew about this and weren't telling people yet. So these are the smiles of people in on a big discovery. We're almost done. Before we wrap things up, I'll comment on the future of what we do next with gravitational wave astronomy. The detection of these gravitational waves from GW 150914 occurred in just 16 days of data. And this implies that if we continue to analyze LIGO data, which will be ongoing and we'll continue to be reporting on, one might expect that there could be other gravitational wave signals in this data. And as LIGO continues to take better data, that we will see more and more detections. As the sensitivity of the detector improves, it may even in fact reach a point where we can detect these at a rate of about 1 per day. In addition to detecting black holes, we have the possibility of detecting other gravitational waves, for example, from binary neutron stars, isolated neutron stars. And this is an exciting moment to be following science as we are witnessing the birth of a new field of astronomy. I'll now pass the microphone opportunely to Yuri as he catches this banner. And he will give us a little introduction to a video right before we open for questions.
Okay, I think it's... I think after looking into the future, which is very interesting, the future of gravitational wave astronomy, totally new branch of science, it's also interesting to look into the past and to pay homage to the pioneers, people who had the vision in the late 70s, early 80s, And three particular founders for LIGO projects stand out, which are Rainer Weiss at MIT, Kip Thorne, and Ron Drever at Caltech. So these are the people who have basically devoted their considerable talents and their whole careers to this field without it, knowing that there will be success, and managed to convince many, many people, including some of us, to follow in their path. And now I want to show you the movie.
I came to Caltech in 1966 on the faculty, working in relativity. I began thinking in great detail about the future of gravitational wave physics and astronomy. Ray Weiss had been the primary inventor of the laser interferometer gravity wave detector. And his classic paper, written in the early 1970s, just lays it out and says, here's what you have to deal with, here's how you deal with it.
The important thing to do in this field was to do experiments to test the theory. And those are hard experiments because it turns out gravity, relative to all the other forces we know about, is a pipsqueak, it's a nothing.
Between 1980 and 1983, NSF funded Caltech to build a 40-meter prototype. And NSF funded MIT to do a feasibility study. So each of these efforts then, running in parallel, became crucial inputs.
In 1989, we made the proposal to build LIGO. That was a Caltech-MIT joint proposal.
And in 1992, NSF, after very careful review, said, okay, we're going to go forward with this, we're going to fund the project. And this was a bold thing. I mean, NSF took a bold step.
NSF bought in because they had faith in Barry Barish, the most brilliant director of large projects that physics has ever seen.
He immediately saw that some of the things that needed to happen should be happening quickly, like you need to build buildings, you need to build the observatories. And it took years. Hanford got started first, then Livingston. And then, of course, once the facility's constructed, then you have to start putting in the detectors. In 1999, there was a dedication ceremony. The interferometers were working. They weren't working at anywhere near their design sensitivity. There was a lot of work that needed to be done before we were ready to go into the first observing run. Nobody had ever made something like this before, so there was a lot of technological challenges that needed to be overcome. Barry Barish realized that if you're building these big interferometers, you better have a community.
The LIGO Scientific Collaboration is about 1,000 people. We all want to detect gravitational waves. We all want to start doing gravitational wave astronomy.
We don't have two collaborations saying who detects it first, who detects it better. We work together.
We ran our initial detectors from 2002 to 2010.
We saw nothing. Now, you say, well, that's a terrible defeat. That's not true. The LIGO Scientific Collaboration was in existence, and they were deeply involved with the data analysis and tracked down everything that we didn't understand about that detector and found out what it was. We had already proposed that in the 1989 proposal, that we were going to do a two-stage thing. We would build the initial detector, and then we would build a follow-on detector with the experience we'd gotten from the initial detector called Advanced LIGO.
We rebuilt our detectors. We've been redesigning them for about 12 years.
So we have more light, better suspensions, and better isolation from the ground, and it's that combination that allowed LIGO to become 10 times more sensitive.
It was Monday morning, September 14th.
I knew that there was something going on because I subscribed to the logs.
This particular log pointed to something that looked like it might actually be a gravitational wave.
What I saw is what's called a time frequency plot, called a chirp. And it was strong. It was unbelievably stronger than anything I expected to be a first detection. It was so strong you could see it by eye. And here was the chirp at Hanford, Washington, and there was the chirp at Livingston, Louisiana. And I thought, my God, this looks like it's it.
It was just perfect. In fact, it was almost too good to be true. When I looked at it, I said, somebody must have done something wrong and injected a signal.
Nobody right away believed it. Everybody thought it was a fluke. It was too good. And it took us a while to get to the point where all of us believe it.
It's monumental. It's like Galileo using the telescope for the first time.
When our descendants look back and they ask, what is the legacy of that era for humanity? I think it will be rather similar to us looking back on the era of the Renaissance when we say, well, the legacy was great art, great music. And so I think LIGO and gravitational waves, along with the electromagnetic study of the universe, will be a huge part of our legacy for future generations.